Oh, okay, okay. Mhm.
Hi. So today we have Amanda Priestley from University of Texas, uh, and she's going to be talking about a probabilistic parking process and labeled IDLA. We're really excited for this talk. Before we start, let us recall our three guidelines. We are all learning, everyone has something to contribute, and no one has all the answers. And with that in mind, Amanda, take it away.
Awesome. Thank you guys again. I want to thank the organizers for inviting me to give this talk. I'm really excited to be here and talking about this project. So this talk is going to be based off of joint work with Pamela Harris, Thiago Holpen, Carlos Martinez Mori, Keith Sullivan, and Per Wagenius. And this was started at the 2024 GRWC at the University of Wisconsin in Milwaukee. And so I know that there's some people here that are familiar with parking. So hopefully the beginning of the talk isn't too slow, but I'm going to kind of go in detail because I think our contributions are kind of might feel very natural after if I can get this first part right. So what I'm going to call the classical parking process is a parking process which was introduced by Konheim and Weiss in 1966. And the idea is to consider a sequence of n cars where n is just the set, where n is a natural number. And we're going to consider each of the cars being given a label in the set, 1 through n. And they're going to be parking in a parking lot full of labeled sites. And we can consider the parking lot to be equivalent to just the line segment 1 through n. And so initially, each car is going to record its preferred parking spot in the preference vector alpha, and alpha being like alpha 1 through alpha n. So each car records a preferred parking spot, and they only have a single preferred parking spot. And alpha I, of course, is going to be the preference of car I. So the cars are going to enter the street from left to right, and they're going to attempt to park in increasing order of their labels. So car 1 is going to park first, car 2 is going to try to park after, and so on. And there's a rule which they have to follow in order to describe how they try to park. So on its turn, if car I's preferred spot is unoccupied, then it's able to park straight away in its preferred parking spot. Otherwise, the car has to continue on to try to find the nearest open parking spot to the right, and it will park there. But if there's not such any nearest open parking spot to the right, then the car will just exit the street and is unable to park. So the set of preference vectors, which allow all of the cars to park, and they don't necessarily have to park in their preferred parking spot. They can park anywhere as long as they're able to find a spot. And this set of preference vectors are called parking functions. And we'll denote the set of parking functions by this PFN. So parking functions have been studied pretty intensively, and this kind of in the enumerative combinatorics community, and this all started kind of when Konheim and Weiss proved that the number of parking functions of length n is going to be n plus 1 to the n minus 1. And please feel free to stop me if anybody has any questions at any time. Oh yeah, so first I have this little picture just to make it more explicit. So car I on its turn is gonna come around to its preferred parking spot, alpha I. But if there's a car already parked there, like there is in this example, then it just has to look for the nearest parking spot to the right. It'll try something over here. But if there's nothing, then I drew this volcano to illustrate that like it can't try anything else. It just has to leave and it can't try again. So its attempt to park is officially over. So here are some simple, but I think they're illustrative examples of what some parking functions. So the all ones preference vector is going to be a parking function. And in this case, the first car, we could just quickly walk through. The first car will park in spot 1. The second car also wants to park in spot 1, but it's filled by the first car, so it'll park in spot 2. The third car wants to park in spot 1 as well, but it can't, and both 1 and 2 are filled at this point. So it will park in spot 3 and so on and so forth. And then also any permutation is also going to be a parking function because the cars don't actually have to compete for parking spots. They can just park directly in their preference right away. Okay. And one example of a non-parking function is if all of the cars prefer the last parking spot. In this case, the first car is able to park straight away, but then all the other cars prefer the same spot, and so none of them are able to park. The second car will try to park in spot N, but it will just have to leave immediately because it can't. And this is by the classical parking rule. Okay. So going forward, what will be important to think about is what happens when we fix a particular outcome of the parking process. So, and what I mean by that is, like before, I kind of mentioned that the set of permutations are a subset of the set of parking functions, but we're going to think about a different subset of parking functions. So in particular, we're going to be looking at the subset of parking functions whose outcome permutation is the identity permutation. And by outcome permutation, I mean the order of the parked cars at the end of the parking process. So assuming I start with a parking function, I want to essentially map each parking function to a specific outcome. And so the subset of parking functions I'm interested in are the subset of parking functions who map to the outcome, which is going to be the identity permutation. So just one more explicit thing is like, okay, car 1 is going to park in spot 1, 2 is going to park in spot 2, and so on and so forth. And so we're going to use this notation PFN and then identity to represent this set of parking functions. And so actually we have a succinct characterization for these type of parking functions. And I think this is probably was known already, but this is just something we included in the paper, and we can go over this proof because it's very quick. But if you have a preference vector in which belongs to this subset of parking functions, or it does belong into this subset of parking functions if and only if it satisfies the property that alpha I is at most I for all of the entries. Okay. And I'll go on to just do the quick little proof. So we can see that, okay, if we start by looking at something which we know is a parking function and it has the outcome being the identity permutation, well, it can't possibly be that alpha I is greater than I, because if the preference was greater than I, then that would contradict that the outcome would be the identity, because if the car did park, it would only be able to park in some spot which is greater than I. So that direction is really easy. For the other direction, there's an alternative characterization of parking functions as being the subset of vectors which satisfy this property. And this just says that the number of entries whose value is at most I is going to be at least I. And by this assumption that we have, or this condition, I should say, this condition implies that this is true, that this holds. And so we know that if we assume this condition, then we know what we have is going to be a parking function. And then we can also know that the outcome is going to be the identity permutation, and this will follow just by an induction argument. Like if we, strong induction, if we assume like, okay, all the cars before park in all the occupied spots before, well then the next car, if its preference is at most I, can only park in spot I. Okay, hopefully that makes sense. Okay, so right, just something to note is that there's a subset of parking functions called the subset of weakly increasing parking functions. And so these are like a notable and I should say they've been previously studied a lot, subset of parking functions who have the outcome being the identity. And so for the set of weakly increasing parking functions, these are actually have the definition that it's a preference vector whose entries have this property that alpha I is at most I, and it's weakly increasing. So it has the same property that we're interested in, it's just in weakly increasing order. And we're going to use the subset BF up arrow N to denote the set of weakly increasing parking functions. Okay, so here is another picture. So again, one parking function I mentioned earlier was the all ones parking function. And this is actually an example of a weakly increasing parking function. And again, we can see that the outcome is the identity because in this case, again, kind of as I went through before, car 1 would park in spot 1, car 2 parks in spot 2, and then on car 3's turn, it also prefers 1, but 1 and 2 are filled, so it'll go directly here. But then more generally, for if alpha I is at most I, then we know on car's 3 turn, it could have car 3's turn, it could have only parked in preferred one of these three spots. And if it's a parking function, we know that these two things are going to be filled by the time car 3 parks. So then the only thing left is spot 3. So this is kind of a picture proof of kind of what was said earlier. So with this kind of background in mind, now we can kind of move on to talk about probabilistic parking protocols. So I'm going to introduce one which is new, but it's kind of not really new, and I'll explain that later. So how the parking protocol that we studied, which is going to be it's going to be the same, very similar to the classical parking protocol, as in we're still going to have n labeled cars, and they're still going to be parking on a parking lot with labels 1 through n. And then the case of a successful parking is still the same. So on its turn to park, if car I's preferred spot is unoccupied, then it still is going to be able to park directly in that parking spot. Otherwise, if its spot is unoccupied, or if its spot is occupied, sorry, then car I will perform a random walk starting at its preference, where it will take one step forward with probability P and one step backwards with probability 1 minus P, which I'll call Q. And it will continue this process until it parks in the first empty spot, if any. So there are some details I still need to flesh out because this can't really describe all the cases, but this is kind of what I'll call like the base parking process that we're thinking about. Okay, and more pictures, of course. So again, this is kind of what we're saying is that, okay, on car I's turn, it'll go directly to its preference. And if it can park there immediately, great. But if it can't, because somebody else is in the parking spot, it'll take one step forward with probability P and one step backwards with probability Q, or 1 minus P. And this will happen every single time it encounters a parked car in the parking lot. Meaning if in this step, it takes one step to the right and this is still filled, it will again do the same thing. With probability P, it'll go forward, and with probability 1 minus P, it'll go backwards. So I've illustrated here something which is kind of to be suggestive of what's to come, is that, okay, one thing you can think about is what if the scenario on the ends is the same as in the classical parking process, meaning if I go off the edge, if I take a step here with probability P, then the process is over for that car. It can't continue to park. And then the same thing would be true at this other side of the parking lot as well now. But I'll talk about the fact that we can actually do several different things. In particular, what we considered in our paper is this case of open boundaries and this unbounded model. And the open boundaries is kind of the case I just described, where if you're on point N or site N in the parking lot, and you take a step forward with probability P, then the car can't continue to try to park. It has to leave the parking lot, and that's the end for that. And the same thing is true if it takes a step to the left from spot 1. The unbounded model is a bit different. In this case, so we can think of the parking lot as still being the set of sites 1 through n, as in the cars can still only park in the set of sites 1 through n, but the car is allowed to kind of wander about infinitely on either side. Not really infinitely, but it can go off as long as it like, as long as it returns to park in the set of sites 1 through n. So a car going off to infinity in this case would be bad, because in this case we think of like the remaining cars don't really get to park because this car just went off, and the other cars actually never start to be able to park. So that's kind of the difference between these two models. We also, things we didn't consider, but which I'll describe later why, but which also are options to consider, are if you had a circular boundary, so periodic boundary condition, so you're now parking on the circle, or closed boundaries, which is similar to the case of open boundaries, but in this case, you can think of the endpoints as being kind of having bumpers on the ends, meaning if a car is in position N and tries to go off, that move is actually canceled, and so it just stays where it is until it is able to take a step backwards. And the same is true on the other end. If it tries to go off from position 1, if it tries to go off the left end, that move will just be canceled. So those are two other options. Today, I'll be giving results for the open boundary case. And some comments about this case is that if you set P equal to 1 in this process, you actually recover the original parking process of Konheim and Weiss. And then if you set Q equal to 1, this is actually equivalent to running, like you could think of it as running the classical parking protocol backwards when you think of it as starting from the rightmost end of the segment and then going kind of left. The motion is then fixed to go left. Okay. So then we kind of want to ask, like, well, what are we interested in studying about this model? What question are we interested in? And so in the case of the classical parking process, Konheim and Weiss were interested in the number of parking functions or the number of preference vectors which allow all the cars to be able to park under that classical parking process. But in our case, actually, each preference vector, it has some associated probability with it that it is able to park. So, and these probabilities are dependent on P and Q now. So rather than having a set of parking functions, a set of things which make it so that all cars are able to park, every vector has some probability which with which it is able to park. And that probability might be 0 or it might be positive. So the question we're interested in now is, given a preference vector, so fix a preference vector, then what is the probability associated with that particular vector that it allows all of the cars to be able to park? When you start our probabilistic parking protocol with that being the set of initial preferences. And then the second question we want to know is, if we assume all the cars are able to park, how long would this process take? Brief water break. Please feel free to ask any questions if you need any. Okay. So I'm going to kind of, that's like kind of a general question that we could ask, but what actually we end up looking at in our paper is, what if we specifically fix our outcome permutation to be the identity permutation? And we ask that similar question. So what if we start with a preference vector whose outcome is going to be the identity, and with what probability does this allow all the cars to park under our probabilistic parking protocol? So this is a bit of a weird question, because what I didn't say before is that actually everything in this set here, that everything which parks with the identity permutation in the classical sense is also the only subset of things which would allow everything to park in this probabilistic setting as well. Because of the way that our process goes, because of the rule we have for the motion of each car, there's no other preference vector in the set end to the end, which, if everybody parked, would allow them to all park in the identity, the order of the identity permutation. So we can really just restrict ourselves to looking at this set, and then we say, okay, if the thing parks with positive probability, the outcome is going to be definitely the identity permutation. And so, and then the next thing we ask is like, okay, if we assume all the cars are able to park, again, how long does this process take? So back to these kind of two things I talked about, these two boundary conditions that we don't actually consider. So the reason why these aren't, I don't want to say they're not as interesting, but the reason we weren't as interested in them is because in the case of the periodic boundary condition, this is kind of clear to see, everything actually parks with probability 1, because the cars will eventually make their way around the circle. No matter what P and Q are, they'll eventually kind of make their way around, and then everything will be able to park with probability 1. With closed boundaries, similarly, if you assume n is fixed and then have some reasonable if you have some reasonable case of P, then also everything should park with probability 1. So one thing I want to comment on is that it still would be interesting to consider the expected time that they would take in these two processes, or these two different boundary conditions. So now I'll talk about some like kind of history or like related parking protocols. So this project was something I proposed to work at at the 2024 DRWC. And at that time in the world of parking, there appeared to be very few parking protocols which actually introduced randomness into the protocol itself. There are a lot of results about parking on random structures like random trees, Galton-Watson trees, or frozen Erdős-Rényi graphs. So you take an Erdős-Rényi graph conditioned to be some size, and so essentially sampling a random graph from this distribution. And so there was a lot of work in this area, but in comparison, there seems to be relatively few projects that look at what happens if you actually change the motion of the cars to be probabilistic. So the paper that motivated our paper was actually this one of Dermick et al. And this served as inspiration for our parking protocol. It's very similar, and the real difference is that if a car fails to park in their parking protocol, then with probability P, it will actually continue on as in the classical case, meaning it will continue to search for the nearest open spot to the right. So it only invokes randomness one time. And then with probability 1 minus P, it will try to find the nearest open spot to the left. So it basically runs the classical parking protocol backwards. So in this paper, randomness is only invoked one time, and that's to decide whether or not I continue on in the forward direction, as in the classical parking protocol, or if I continue on in the reverse direction, as in the classical parking protocol. So
A
that,
small
yeah,
clarifying, just question. So when
yeah,
you say it's invoked one time, is it invoked one time for each car, or once when you start going backwards and everything starts going backwards?
great question. It's one time for each car. Yeah, so it's like each car that fails to park. So if a car fails to park, you can think of it as flipping a coin, and if it's head, it goes to the right, and if it's tails, it goes to the left. So in their process, they flip the coin only one time, and that's one time per car. So if a car fails to park, it flips one coin, and that sets what it does for the rest of the parking protocol. For ours, you can think of the car as flipping a coin each time it comes across a spot which is still filled. So every time it hasn't found its open spot, or basically until it finds its open spot, it is continually flipping coins to make these like more granular decisions about, do I take one step left or one step left or one step right? Hopefully that clears things up. Okay, great. So, however, if we go to the world of interacting particle systems, which I'll kind of explain what this is in a second, our parking protocol is not exactly new, and it's actually a special case of a particle system called IDLA, which stands for Internal Diffusion Limited Aggregation. So I should also say that I was kind of motivated, like I'm mainly a probability person that loves like the interactions of probability and combinatorics. So I was kind of motivated by studying other interacting particle systems. And so, yeah, our model was kind of motivated by this. And an interacting particle system, one can just think of as you have a set of particles and they're moving around maybe on the lattice or maybe on the line or maybe on the line segment, as in our case. And you have some rule for how they interact. Maybe the rule is that they'll bop around and maybe they're moving according to a random walk. And maybe you have the rule that no two particles can actually exist on the same site. Or maybe you have the rule that they actually stack on top of each other. So there's many kind of models motivated by physics that could be considered these interacting particle systems. And so our parking process is actually an example of a special case of this model called IDLA. So IDLA is actually a model of growth, which was introduced by Diaconis and Fulton in 1991. And the model was originally defined on like the d-dimensional lattice. And the dynamics are exactly the same as our process, meaning what we have is a set of particles, and I'll talk about it on the line. So we can think of, in their case, they're thinking of the set of particles being dropped at position 0. And so once a particle is dropped at position 0, it will move around according to the rule of a random walk until it finds the nearest open space. And so particles are continually dropped and they kind of filter out from 0 to occupy sites like this. And that's why it's called kind of a model of growth, is because if you think about the set of sites which become occupied, they're kind of moving out from 0, and then the set of sites which becomes occupied kind of grows like this. Or if you're in the lattice, it grows kind of outward. And so there's a lot of research on this model, and a lot of focus went towards studying like limiting properties of this model. In particular, they want to one like early result was showing that the limiting shape of this process is actually a ball. So as you kind of continue to add the particles, which makes sense, kind of if you're looking on the lattice, then you have this kind of the set of occupied sites is going to grow outwards to like occupy this like a ball shape. And so one can actually think of our protocol as actually an instance of labeled IDLA on the line segment. So one thing to kind of uh, distinguish our two or distinguish this from like the classical sense is that we are like specifically interested in keeping the each car or particle to have a specific label. So we have car 1, car 2, car 3, this kind of thing. In their case, they were kind of looking at just unlabeled cars or unlabeled particles. You can't distinguish between the two. So they're kind of just looking at the limiting shape in this process, but they're not really considering which particle ends up where we are looking at that. So just some comments on this model. So it's a very interesting model in the probability space for several reasons. And first of all is that in their original paper, Diaconis and Fulton show that this model is abelian, meaning that actually the final configuration of the particles on the line or on the lattice doesn't actually depend on the order of the particles, the order at which the particles move. And that kind of sounds a bit contradictory to what I just said. It's like, oh, we want to distinguish the particles, but what that means essentially is if we erase the labels on all of our cars, like the probability that, oh, and I have a slide for this. I should stop using my hands. So like the probability that this set of sites is occupied and like these are left empty, I should say, or maybe this entire thing becomes occupied is actually equal to this probability that all the things become occupied. And it doesn't really matter which, and I gave the particles colors to distinguish them, but it doesn't actually matter which one goes first. These probabilities will be equivalent. But why we keep the labels is because we are specifically interested in looking at like a specific one. So in our case, we actually are keeping them as distinct things, but just know that if you're interested in only the probability that these sites specifically are occupied, this is actually the same regardless of what the labels are. But we're interested in a bit more granular information, if that makes sense. And another reason why this is an interesting model is because it actually exemplifies a physics phenomenon called self-organized criticality. And I should speak very loosely on this because this is a complicated thing. And so but this is just like kind of a very loose sentence about it, is it's a phenomenon where this system appears to undergo a phase transition, but it's not by way of fine-tuning parameters in the model, but it's mainly actually by the dynamics of the process itself. So you can think of this as being like the fact that the set of sites becomes occupied is not as much, not as sensitive to the parameters, but it's more happens naturally as by way of the car's motion. If that's hopefully that's a good simplification. Um, yeah. So some more kind of comments is that this model was actually generalized to be this something called the golf model by Barin. So this is actually another recent paper. So her generalization, and you can think of it, if you want to think about it back in the parking language, is if you took our probabilistic parking process, but then you don't allow all of the spots to be parking spots at the beginning. Maybe you put some trees in the parking spots or you put some barriers so cars can't actually park there. So this is a bit more general because we allow the initial configuration to not necessarily be all empty sites where the cars can park, but now we have some blocks where nobody can park there or something like this. So there's a bit more generality here. But in their paper, they also study a parking process which is equivalent to IDLA on the cycle. And before I kind of mentioned about, oh, how this parking process on the cycle is not that interesting. And it's not that interesting when you look at the same number of cars as spots. But her question, she looked at actually strictly more parking spots than cars. And then she's interested in, okay, where do the cars actually end up parking? So what is the distribution of the empty spots that are left over at the end of the parking process? So we know that there's some stuff that's going to be filled, but we also know we have more spots than cars. So we want to know, where do these gaps happen? Or that's what she was interested in. And because she's not interested in actually which car parks where, she still is like able to kind of make use of this abelian property. And so I briefly want to make a comment to thank Alice Contat and Availo Tarsky, who both kind of introduced us to these models like the IDLA and the GOLF model. And so I also want to make one more comment, because I know if you're not that don't have a lot of fun in probability world, there's actually a completely like algebraic study of these type of processes as well. So if this is your flavor, this slide is for you. So after publishing our work on like arXiv, we were made aware that Nadeau and Tawari actually study a generalization of IDLA, which is equivalent to our unbounded model. And then Nadeau actually went on to formalize this as a parking process in this paper here. And so what's interesting is that they actually answer the question of, okay, if you start with a general preference vector and alpha in n to the n, what probability does this park under this parking protocol? So they answer that question in full generality. They don't really specify at all like a fixed outcome permutation like we do. And our works differ significantly, because our paper is kind of more from a classical probability perspective, but they actually use strictly algebraic methods, and they're able to get the probability of parking in terms of something called these remixed Eulerian numbers. And then they show that something called these Postnikov trees can be seen as recording the past states of the process. So if this is kind of your flavor in your language, then this kind of result might be really interesting. And I also just found it really interesting that you can study this problem, which sounds like completely probabilistic, but like entirely using like algebraic methods. So it really kind of shows that this is a kind of an interesting problem for both worlds. Like you really don't, I don't think you need any probability at all to understand what they're doing in this paper. So yeah, other than of course like what probability means, the really basic stuff. But the things that they don't consider is they don't really consider the expected time it takes the protocol to complete. And yeah, ours is different, as in our paper ends up being different because we look from this classical probability perspective. Again, we're looking at fixing specific outcome, and we consider a different boundary conditions. And this is like among some other things which are different. But yeah, just to highlight this. Okay, so there's a lot of introduction, but now I can go on to the results if nobody has any questions. Okay. This is one of our main theorems for the open boundary model. So if we start with a preference vector, which is in the subset of parking functions in the classical sense, whose outcome is the identity permutation, then we know that the probability that all the cars park is actually given by this thing, which is, you can see it has this dependence on the preferences. If P is equal to a half, it's actually just the product of all the preferences divided by n factorial. And on the other hand, it's something a bit more nasty looking, which is something which depends on both P and Q, and again, like the where you start and actually where you want to end up parking. Like you can actually see this as the difference between your starting position and where you want to end up parking. And this can be kind of seen as like a probabilistic version of this like this notion of displacement in parking functions, if people know what this is. Yeah, so that's kind of what I want to say about this. And this is our kind of second main theorem, is that if we want to consider the expected time that the parking process takes, again, starting with conditioned on the fact that all the cars are able to park, and that we know that we're starting with this preference vector, which is a parking function whose outcome is the identity permutation, then if p is equal to half, we have this expression here, which also seems kind of like something combinatorial here. You have like, it's the difference between where it wants to end up parking squared and where it starts squared. And then, but then in this case where p and q are not equal, this looks just like kind of something gross. So I don't really have, there's not really much to say about it in that case. So I'll kind of go through a proof sketch at this point. So something we rely heavily on is the fact that our outcome permutation is fixed to be the identity permutation. And also we use this chain rule of probability, which is actually down here, and I'll describe it a bit more. So if we let AI denote the event that the ith car to arrive parks in spot I, you can think of this as just, okay, the ith because of what we're starting with the preference vector whose outcome is the identity in the classical sense, we're just saying this just means actually that the car I parks. So this chain rule of probability, what it says is that, okay, if I want to look at this, the intersection of all these events, so I want to look at the probability that all these things happen, that all of the cars are able to park, then that's just the product of the first event times the product of the second condition on the first and the third condition on the first and second, and so on and so forth. So what this kind of means is I can actually look at this process in the very natural way as like, okay, I can condition on the thing I want to happen having happened already. So I can just condition on the fact that car one is able to park, and then I can just take the product of these things. And then when we begin our probabilistic parking protocol with this type of preference vector, this term actually becomes so nice because this probability, when we condition on all the previous cars parking, is just equivalent to the probability that car I's random walk hits position I before hitting position 0 when we start the walk from position alpha I. And so this is actually a classical and well-studied problem in probability called the gambler's ruin problem. And in the language of that problem, the gambler's ruin problem is basically saying we want to know the probability that a gambler wins I dollars when they start with alpha I dollars before being ruined or running out of money, so you hit 0. And then I can give a bit more of a picture intuition. So again, if we start with something, for example, that's just a weakly increasing parking function, which is a parking function whose outcome is the identity, basically, if car form wants to park, it's kind of allowed to do whatever it wants here and go on and on. But if it wants to park, the real thing it does is it has to hit 4 before it hits 0. That's like really what has to happen. So this is kind of what then the gambler's ruin like kind of argument goes on to compute this. This what is this probability that a random walk that can pull around here hits this spot I before going off the edge and hitting position, we'll call this position 0. And so this problem is classically solved using writing a recursive formula for the probability, and then solving this linear recurrence relation. And I'll just go back to show, so we can, for example, the probability of hitting 4 before here, when I start from 2, is the same as, okay, if I take one step to the right, so I multiply p times whatever the probability is at this point, or it's the same as q times whatever the probability is here. So that's the recurrence that you end up looking at. And so in the case of the work of Nadeau and Tori that I mentioned earlier, their algebraic methods actually kind of end up giving you back the gambler's ruin recurrence relation in the form of like, these ends up being the coefficients of some polynomial. So it's actually really interesting. Yeah. And so the computation for the expected time to park can be done similarly in this, like you again write the recurrence relation for the expected time to park, and then you solve this linear recurrence relation, and that gives you what you want. But in our paper, we also give a combinatorial solution, which comes about by enumerating the number of paths when you of a fixed length when you start from position alpha I. So in particular, any path of R right steps and L left steps will have the same actual probability because we're just taking P to the number of right steps times Q to the number of left steps because each step is independent. And in addition, any path starting from position alpha I and ending at position I must take it twice as many right steps as left steps because anywhere it goes back, it will have to travel that distance back to get to where it wants to go. So these are kind of some motivations to help understand how we do the counting. And then again, we can give a recurrence relation which enumerates the number of paths starting from position alpha I and ending at I. And then the terms in this sequence actually end up appearing in this paper of Nemeth and Szalay, and they call these things something related to like zigzag paths. So the terms in the sequence end up appearing here. So this combinatorial approach, we kind of just leave things in terms of this sequence here. So yeah. Oh, no. Okay, no questions. So in the beginning, I started off by saying, okay, we do this we're fixing a preference vector who is a parking function whose outcome is the identity permutation. But note that this argument actually works exactly the same way when you think of something which is, for example, a weakly decreasing parking function, or what we'll call a weakly decreasing parking function. So a weakly decreasing parking function is what we mean it to be is a parking function which would be considered weakly decreasing if you were to run the parking process from starting from the right side to the left. Meaning, okay, the first car is going to park in spot n, the second is going to be park in spot n-1, and so on and so forth. And so in particular, our arguments work for any parking function whose outcome permutation is this n, n-1, n-2. And this is also characterized by the set of vectors whose ith entry is at least n minus I plus 1 for all I. Right? So we have this, essentially, our argument works as long as you growing the number of parked cars from the right-hand side, or you can grow the number of parked cars from the left-hand side. And in particular, this argument of, fixing the outcome doesn't exactly work in this way when you consider like things having gaps, or if you, for example, when all the cars, as in the IDLA classical process, all the cars are dropped on the same site. Well, now the cars have we actually have a distribution over where the cars end up, if that makes any sense. So for example, if I consider, let me wonder if I can, if I have any room. Oh, okay. I'll just draw a very small picture. Hopefully it's helpful somewhere. Okay, if I can zoom in. Great. Okay, so if I dropped all the cars on spot 0, well, the first car will park immediately in spot 0, but now with probability P, car 2 will park here, but with probability 1 minus P, the car would park over here. And actually, so now when we go to run the process when we start with the third car, there's actually a distribution over what this configuration looks like. It's either going to look like this, or it's going to look like, I should be consistent with my colors, or it's going to look like, okay, sorry, this. And so this being position 0 and this being, so we're either going to have one car parked to the right with probability P, or one car parked to the left with probability 1 minus P. So now, again, in each step, we now have a distribution over what the state of the parking lot is. So this is why you can't exactly just straightforwardly why our argument doesn't directly apply to this kind of setting. You have to deal with this. Okay, some other results I want to comment on that are actually included in our paper is I'd give analogous results for the unbounded model. And these these results similarly rely on Gambler's ruin computations, but then on the line Z. But we're lucky that these kind of computations had already been done by McMullen, so we could actually use these directly. But we want to note that in the unbounded model, if P is from 1/2 to 1, then actually the car any car will park with probability going to 1 as with probability going to 1, the car will hit position n in a finite amount of steps. And it won't run off to infinity, or negative infinity, I should say. In addition, we also proved that the parking process with open boundaries is negatively correlated. And what that means is we show that the probability that an earlier car parks only makes it less likely that later cars will be able to park for the model with open boundaries. And this should kind of make sense, because if we have that, okay, car, like the first 5 cars park, well, that means that we have 5 less spots for any later car to park. If none of those cars park, then there's many more spots that a car could possibly park in before leaving the segment. So this should kind of give you the intuition that, okay, the probability of a car parking should only actually decrease, or stay the same or decrease, as the cars before it actually park in those spots and occupy the spots that it wants to occupy. So some other things we look at are some statistics of weakly increasing parking functions, such as we look at what is the distribution of the last entry, the distribution and the expected value of the last entry. So if we start with something which is a weakly increasing parking function, what probability is the last entry going to be, like 5, for example? We give formulas for this. In addition, we also give the distribution of the set of lucky cars of a weakly increasing parking function. And more specifically, we say, okay, fix some subset of the numbers 1 through n. So let's say fix 1 through 4. We give you the probability that these cars are lucky when you start with a weakly increasing parking function. And we also give you the probability, the distribution of the number of lucky cars. So both you can fix a set, a specific set, and ask what is the probability that this set of cars is lucky. But you can also fix a number of lucky cars and say, okay, what is the probability this number of lucky cars is, this number of cars is lucky? Where I should have said that a lucky car is a car that's just able to park directly in its preferred parking spot right away. For example, the first car will always be lucky because it will always get its first choice. It doesn't have to compete with anybody. So this is kind of, we also show things related, statistics related to that in this paper. Okay, so lastly, I'll give some open problems. So, and again, just to highlight that the talk talked about like probabilistic methods to look at this, but then there's really no restriction to say that this is the way you would have to do this, because as I kind of mentioned, it seems that algebraic and probabilistic techniques are equally as like valuable in this case, kind of depending on which question you ask. So kind of if you ask the right question, you really could get away with not using any probabilistic techniques and kind of just looking at this from an algebraic perspective. So so one open question one could consider is, what if you have more cars than spots? So the idea is if you have more cars than spots, eventually, if you assume appropriate values of P and Q, the parking lot should become full. And this is because like, meaning like, okay, and I'm mainly considering what if you have the open boundary model. So if cars can leave the segment at either the left or right endpoints, well, some cars might fail to park. But eventually the idea is if you run enough cars through the process, the lot should eventually become full. And so the question is, how long would that take? Or what number of cars would we have to put through the process to where the lot becomes full? And then the next question is, if we want to maintain the label of the cars, what is actually, we look at distribution, like the probability that car I ends up in spot J, where like car I might be like the 10th car to go through. So what is the probability that the 10th car ends up in position 3, for example? And then another question you could ask is, okay, what if you have fewer cars than spots? So this would be like in the case of Varin, who did the golf model, but she did this on the cycle. So you could also ask the same question on the line or elsewhere, like what happens if you have less cars and more parking spots, and then you want to look at like what is the distribution again of where are the occupied sites, are they all here and here and here? Like with what probability does this kind of configuration come out? Another question is, and I've been asked this like every time I've given this talk, and so I think this is actually that says maybe that it's a popular question that somebody should look at. Is that, well, what happens if the probability P depends on which site you're on? So, for example, what happens if, maybe draw a small picture. Um, so what if from like the probability, if this is filled, of going forward from here is actually P1, and what if the probability of going forward from spot, let's call this spot 1 and spot 2, going forward from here is this P2, where P1 and P2 might be different. So now what if you have like a vector of probabilities associated P1 through Pn with each spot, which tells you, okay, with what probability you move forward from that particular spot. And you could also make this dependent on the car. Like, okay, maybe the car gets a particular probability, forward probability associated with that car. Maybe some cars are unlucky or unluckier than other cars, meaning they go forward with higher probability or something like this. So you could vary the probability P and not just leave it fixed for the entire process is essentially what this bullet point is interested in. I mentioned other boundary conditions, and while I mentioned that they're not so interesting for the probability question, you could still also ask the time it takes to park question for those other boundary conditions. And then the last question is like, what about other probabilistic parking processes? So so far it seems like we have a lot of or we don't have that many parking processes which uh, the steps that the cars take is actually probabilistic. And then the ones we do have seem to be generally based off of like the car moves according to a random walk. But what if you had some other way, some other probabilistic description of how the cars move? So this is another question. And it could either, yeah, it could still be motivated by interacting particle systems, like a classical interacting particle system, or maybe you come up with something which is unique that describes how the cars should move. That's also an open question. So I think that's all I have for today. Thanks very much for your time and attention.
Thank you so much, Amanda. Now it's time for
Thank
questions.
I have a question, but this is I don't know, very minor. You mentioned oh my God, it was like rewritten Eulerian numbers.
Oh yeah, let
Um
me
re
remixed or yeah,
yeah,
yeah.
remixed. Yeah. Do you know what that is? What's
So
the remix? What's
good question. I don't actually know what these remixed Eulerian numbers are, but
yeah,
I will say that actually, so one comment is that if you look at, I should say this. So if you look at, I mentioned before that like our analysis doesn't exactly translate if you think of all the cars being dropped on the same spot. Um, but I should say that this is still actually a gambler's ruin question. Like if I just want to look at what the probability is that these set of spots is occupied, this is still like each car is still doing a gambler's ruin kind of thing. So
yeah,
each, because the set of like let's say these set of car spots, oh, why actually? Yeah, let's say these set of spots is occupied. Well, then I still have, okay, what is the probability it hits this spot before it hits this spot? And that kind of determines how the growth goes.
yeah,
So I know that there's like this kind of like a general gambler's ruin recurrence is related to Eulerian numbers. Um,
yeah.
and there is, I don't know how the remix version looks, but there's actually a paper, something called Weiss Earn. Uh, it's like exact, it's actually they were looking at something about like randomized trials for like drug trials, I think. Anyway, there's something called there's this paper about Weiss Earn, but they show like this general gambler's ruin thing is relate actually like the probability is given by these Eulerian numbers. I'm not sure, I am so sorry, how it relates to these remixed
No
Eulerian
worries.
numbers. Yeah.
Yeah, yeah. Thank you
It
so
is my
much.
PhD, so I can answer your question if you want.
Oh, yes, please, please.
Uh, So I'm a PhD student under NADO.
Oh,
Remixed
fantastic.
unary numbers are you obtain them through mixed volumes of some of the polyhedron of a polyhedron in n dimension, the associahedron. So yeah, they have this algebraic definition as Amanda described, but you can view them through this particular process.
Thank you so much. I feel
And
lucky to have.
they specialize to Alerian numbers, indeed.
Okay. Great, great.
Very good explanation.
Oh, thank you. I feel lucky to have you in the audience to to back me up.
Thanks for the talk.
Thank you. Thank you so much for coming.
More questions? Or if your PhD was talked about in the talk, you can contribute something. I have a question, like a small, about the zigzag paths.
Oh, sure. Sorry. Let me
I
you
think
these
like the
guys?
proof. Yeah, where the
Oh,
proof was.
oh, okay. The proof over like the maybe the the like this guy?
Yeah. So I just want to see if there is like a 20 path starting position from position I. And
Sorry.
I just want to see like if there's a picture associated to it, to like a small.
Oh, a picture for this? Oh, yeah, yeah, yeah.
Yeah.
Okay. So let me think. So for the expected time to the recurrence is a bit different than the or it should be really similar. But in terms of uh so like when we're looking at the expected time it takes to park, we want to the and maybe the I won't give a picture so much, but like look at uh kind of a formula. So let's say I want to fix a path of uh, length k. So I want to do k equals 1 to infinity because there we can, oh, and this is a bad color choice. But so then I want to look at the probability of this particular path times the length itself, or I want to look at, yeah, the expected, uh, yeah, I want to look at the path, times the number of paths because I'm looking at uh, the number of paths that this would that there would be of this particular length.
Mhm.
Well, I guess that's incorporate. Yeah. So because what I should say that we have the number of paths we're looking at times the and then normalized by, oh goodness, I should say. Okay. So for example, because like I said, we have R right steps and L left steps. So I would have like something like P to the R times Q to the L.
Okay.
Um, and then this would be like the probability. And then um, we're looking at uh, that summing over all paths of length 1. So I want to look at the uh, associated, like the number of such paths of length 1. So we'll have some term which is kind of computing the number of paths of length 1. And this will kind of be how it will look like.
Okay.
Yeah. So
That I'll clarify a little. Yeah.
yeah, sorry for the messy.
It's fine. Yeah, but are there more questions?
I kind of have one. I'm not sure if it's a good question or not, but like, what happens or what do you think will happen if you consider cars with different lengths? So,
Oh,
because all of these are just unit interval ones, right? Like they're all the same size and they park in the same size spot. But like, what if a car has like length two and needs two parking spots? Like, I'm sure something would change.
that's a great question. So there's actually, and so I should go back to this paper. So in this, this paper is interesting for that because they show, they actually, when they show that this process is abelian, they actually show that they define like an algebraic operation that is kind of like that this particular like random walk model falls into, where you're growing your set by you have a set of occupied sites on the line, and you're growing by one element at a time. But they also have a more like they prove this for general like growth processes which follow this follow this um, rule, and they also allow for what if you grow by more than one element at a time. And so I think you would have, you might be able to get something by going back to this paper and seeing what they would have to, like what it would give if you look at like the algebraic notion of this process
Right. Okay.
as like just a general growth process. If I think about it from the probability setting, I definitely think things would be different. But again, I think you'd still have like this, it would just be like you would still grow. It's just kind of by how much you would end up growing in each step, if that makes any sense. So I think that would be the main difference.
Okay. Yeah, because I was just thinking like if let's say one car had length 2 and one had length 1, like if they ended up parking in a certain spot, like if
So
if if the parking like spots at the one end don't have enough room for it to park, like the only like it has to move forward in order to park. And
no, that's a good question.
yeah,
Sorry, I misunderstood. But if you
no,
have
that's okay.
different, like each car is able to have different length. Like I think if you fix all the cars to be able to have to have the same length, then I think you should get something which is similar to this.
Right,
If you allow every like the different cars to have different lengths,
right,
then yeah, that's interesting. I'm not sure what yeah, I'm not sure off the top of my head that these classical things would apply. I think you would have to actually, uh, yeah, think about it more specifically. So that's a great question too.
right. Yeah. When I said unit interval, I meant like yeah. You were
Yeah,
correct with the way I said it.
no, 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 no.
Said
Yeah,
it
that
wrong.
totally. No, no, no. My bad. I totally get it. That makes sense.
Yeah.
Questions? There are no more questions, then let's recommend again.
Thank you.
Thank-
I
Oh,
have a question.
Oh, yes.
yes.
Maybe I missed it during the talk, but why did you focus on the parking functions that have identity permutation as the outcome?
So, that's a good question. I think we actually, um, our approach was kind of to look at what we could do by fixing the outcome first. And I think that was kind of, I hate to say it, there wasn't a great motivation. It was kind of just, it felt like very natural to look at. I guess I will say that there are a lot of parking functions papers that do actually look at counting parking functions by fixing outcomes. So that maybe is um, maybe I think this was kind of floating in our heads at the time, is that you can, there are enumerative results where they fix the outcome and then go backwards to count how many parking functions map to this. So I think maybe this was kind of in the back of our minds.
I see. Thanks.
Yeah,
Thank you. Let's thank Amanda for real this time.
thank you.